Hello students. We already know the four basic laws that govern the gaseous state, right? So, let us quickly revise these four laws. Boyle's law tells us that P is inversely proportional to V and can also be written as V is inversely proportional to P. The next one was Charles' law, tells us that V is directly proportional to T. The next one is Gay-Lussac's law, tells us that pressure is directly proportional to temperature. The last one is Avogadro's law, tells us that V is directly proportional to N. So, if I compare the three laws that have the term volume in them, I can get a combined equation, which is V is proportional to NT by P. Now, to remove the proportionality sign, I must write a constant R, called the universal gas constant. Its value varies depending on the units of P and V terms. Now, over here, I can also rewrite this as PV is equal to nRT. This equation is called an ideal gas equation. That can also be written as PV is equal to M by mRT. Now, let us move this molar mass to the left side and volume to the right side. Now, what is M by V? The density of a gas. So, now we have Pm is equal to dRT. This equation is the derivative of the ideal gas equation. And these two are derived from the basic laws which govern the gaseous state. So, as we are done with the four basic laws as well as the ideal gas equation, let us talk about Dalton's law of partial pressure. So, when I am talking about Dalton's law of partial pressure, remember, it is only seen for mixtures of gases that are not reactive. So, let us see a few examples. Now let us first enlist where it is applicable. Nitrogen plus helium. Hydrogen plus oxygen at room temperature. Any gas with a noble gas. A mixture of noble gases. Nitrogen plus oxygen at room temperature. Nitrogen plus hydrogen at room temperature, and likewise. Let us see a few examples where it is not applicable. Ammonia plus HCl. NO plus Cl2. SO2 plus Cl2. PCl3 plus Cl2. SO2 plus O2. H2 plus Cl2 and likewise. To understand Dalton's law, let us take an example. Say I have three containers of equal volume connected with each other that are kept in identical conditions. Now, suppose in container A, we have H2 gas with a total pressure of pH2, while in container C, we have neon gas with a total pressure of PNE. Now, if they are allowed to diffuse in container B, in that case, as all the conditions are identical, the total pressure in container B is Pt is equal to pH2 plus PNE. Why is it so? It is due to one simple reason. If we consider gas behaves ideally, they won't interfere with each other, implying the pressure due to H2 and Ne will remain unaltered, even when they are present together. Thus, we can write the total pressure as the summation of their partial pressure. But wait a minute. Why the term partial pressure? It is a term that is used only when there is a mixture of gases present, because, at that time, the pressure due to any gas will only be part of the total pressure, but not the complete pressure. Now, remember, this law is applicable even when there is a number of gases present in the mixture. At that time, the total pressure will also be the summation of the partial pressures of individual gases. Now, if we have total pressure and mass of gases is known, and we need to determine the partial pressures of the individual gases, then how should we do so? For that, we have a very simple formula. For example, if we take our earlier example itself, then for pH2, it is Pt into mole fraction of H2. And for Pne, it will be Pt into mole fraction of Ne. The pressure exerted by individual gases will depend on the fraction in which they are present. Correct? Now, before going to our last law, let us learn something about diffusion and effusion. Let us first see their definition. Diffusion is the process whereby gaseous atoms and molecules are transferred from regions of relatively high concentration to regions of relatively low concentration. Effusion is a similar process in which gaseous species pass from a container to a vacuum through very small orifices. So, after understanding diffusion and effusion, let us see the last law, which is Graham's law of diffusion. So, in this law, we concentrate on the rate by which the diffusion or effusion takes place. So, the first factor influencing the rate of diffusion or effusion is the molar mass. From the following example, where the rate of diffusion of SO3 and O2 are compared, it can be seen that the rate of diffusion of O2 is higher than that of SO3. The reason is simple: if the molecule is heavier, it will move slowly. Thus, the rate of diffusion also decreases. So, the relation between R and M is R is inversely proportional to the square root of M, which is the molecular mass of the gas taken. For the next factor, we do not have to go far. It is a regular thing which we observe in our life. You might have observed that when someone is cooking food nearby, we can smell it even from our room. However, if you want to smell an ice cream, you have to go very close to it. Why is it so? What is the difference between these two cases? Yes, the difference is in temperature. So, when the temperature is lesser, the diffusion of the gaseous particle is slower. In comparison, the opposite can be said for the higher temperature. It implies that R is directly proportional to the temperature T. Let us see the last factor, which is pressure. To understand this, let us take an example. So, as you can see here, we have two empty containers, each, in turn, is connected with a smaller container where the gas is kept at different pressure. Now, as you can see over here, the rate of diffusion is more in the container connected to a high-pressured gas, while it is less in the container connected to gas kept at low pressure. So, from here, it is clear that R is directly proportional to the pressure P. Now, as we reach the end of the module, let us summarize what we have studied over here. First, we derived the ideal gas equation. Then, we moved on to Dalton's law of partial pressure, which is applicable to only non-reactive gases. And the formula is Pt is equal to P1 plus P2, and so on. The next one is Graham's law of diffusion, which tells us the rate of diffusion depends on the molar mass of the gas, temperature, and pressure. It is directly proportional to the temperature as well as pressure. However, it is inversely proportional to the root of the molar mass of gas. That is it in the module. I hope you understood all the things we had learned in this module. Thank you.